The AeroCar Revolution. Redefining the future of transport. Part 1. The Dawn of AeroCar Technology. Chapter 1. A New Horizon. The morning sky over Silicon Valley glowed with the first rays of sunlight, painting a picture of serene beauty above the bustling technology hub. On this particular morning, however, something extraordinary was happening above the clouds. A sleek, silver vehicle hovered silently, suspended mid-air, as if defying gravity itself. Its rotors hummed with a soft, rhythmic vibration, like a symphony heralding the dawn of a new age. Inside the cockpit, Dr. Elena Rios, a visionary inventor, leaned back in her seat, a satisfied smile tugging at the corners of her lips. Altitude steady at 1,200 feet, the AI system intoned, its voice calm and confident. Wind resistance negligible, fuel cells operating at 97% efficiency. Elena's hands hovered above the manual controls, but she didn't intervene. The vehicle, the prototype for humanity's first commercially viable flying car, was entirely autonomous. She had spent years perfecting its design, pouring her heart and soul into overcoming the engineering and regulatory challenges that had once made flying cars a science fiction dream. Today was the culmination of that journey. The moment the vehicle soared seamlessly into higher altitudes, Elena felt a surge of emotion. Not just for herself, but for humanity. She had always envisioned the skies not as a chaotic battleground of noise and danger, but as a vast, untapped canvas where civilization could paint its next great masterpiece. Activate public mode, Elena instructed. The AI responded with a subtle shift in the vehicle's trajectory. Below her, traffic streamed across bridges and highways like veins in the city's circulatory system. But the roads, as she imagined, would soon be obsolete. Flying cars would unclog cities, give back hours of life lost to commutes, and carve paths of freedom in a three-dimensional world. This was the future she had promised herself, and now it was within reach. The breakthrough moment. And Elena's path to this milestone had not been easy. Years earlier, she had stood on the TED stage, a lone figure armed with little more than passion and a prototype model of her vision. The audience had been skeptical. Flying cars were an old dream, dismissed by experts for decades due to insurmountable hurdles, unstable aerodynamics, energy inefficiencies, and public distrust of autonomous systems. The sky, Elena had declared back then, her voice unwavering, is our next frontier. But to conquer it, we must first create vehicles that are safe, sustainable, and accessible to all. My team is building just that. The cornerstone of Elena's vision lay in a revolutionary eVTOL, electric vertical takeoff and landing, technology, powered by graphene-infused batteries capable of storing massive amounts of energy in compact cells. This breakthrough, coupled with lightweight materials derived from carbon fiber composites, allowed her designs to achieve unparalleled efficiency. Yet, the real genius of the project wasn't in the hardware but in the software. Elena's flying car featured an AI county pilot, programmed to adapt dynamically to environmental conditions, reroute based on real-time traffic, and even predict mechanical failures before they occurred. Over time, the AI could learn a user's preferences, creating a blend of autonomy and personalization that few could resist. The public's skepticism began to wane during the prototype's first public demonstration. On a crisp autumn morning, a vehicle silently rose from a compact vertiport, hovered effortlessly, and zipped across the skyline of Los Angeles. Thousands watched in awe as it transitioned seamlessly between vertical and horizontal flight, landing with the precision of a dragonfly alighting on a leaf. It wasn't just a technological marvel, it was an emotional moment. For the first time, humanity could envision cities without the chokehold of gridlocked streets. Alina's prototype wasn't merely a car, it was a promise of freedom. Building the future of the sky. Of course, there were hurdles beyond the technological. Freedom always comes with responsibility, Alina often reminded her team. Government officials were quick to point out the potential risks. How would flying cars navigate the chaos of an urban skyline? What would happen during storms, or in the event of a system hack? And most importantly, who would be responsible in the event of a crash, man or machine? Alina had answers for all of them. The sky would be divided into invisible corridors, regulated by an AI-driven traffic control system. Each flying car would communicate with the system and with other vehicles, forming a hive mind that optimized traffic flow and minimized collisions. Weather conditions would trigger automatic rerouting, with fail-safe landing protocols in case of emergencies. The hardest question, though, was one of equity. Would flying cars be a luxury for the elite, or a resource accessible to all? Alina's heart sank at the idea of her invention becoming just another tool of class division. She insisted on a dual approach: private ownership for those who could afford it, and a network of affordable sky taxis for the broader public. "I don't want to create a technology that divides us," she said during one heated boardroom debate. "I want one that lifts us all, literally and figuratively." The day the world changed as the first flying cars rolled out of production, their impact on society was immediate. Cities began redesigning themselves. Multi-story parking garages transformed into vertiports. Ground-level streets became lush, green spaces where children played, and pedestrians strolled without the constant threat of traffic. Delivery drones shared the skies with passenger vehicles, creating a ballet of machines choreographed by AI. Yet, as the world adapted, there were growing pains. "People are scared of what they don't understand," Alina said in an interview. Public trust in the technology wasn't instantaneous. Videos of malfunctioning prototypes circulated online, feeding fears of mid-air collisions and crashes. But Alina knew that fear could only be conquered by transparency and education. Her company hosted workshops, simulations, and test flights, inviting skeptics to see the technology firsthand. By the time the first million flying cars took to the skies, the world was irrevocably changed. Alina's vision had gone from a dream to a global phenomenon, and the skies above cities like Tokyo, Paris, and Mumbai buzzed with activity. People were no longer bound by the constraints of terrestrial travel. The air, once dominated by birds and airplanes, now belonged to everyone. As Alina descended her prototype back onto the vertiport that morning, she couldn't help but marvel at how far they had come. She had not just created a vehicle, she had ignited a revolution. "This is just the beginning," she whispered to herself, stepping out of the cockpit. Above her, the sky seemed infinite, waiting to be explored. And for the first time in human history, it truly was. Chapter 2. From concept to reality. The road to the skies was paved with obstacles. For decades, flying cars remained confined to the realm of science fiction, a tantalizing concept that seemed perpetually out of reach. Engineers and dreamers alike envisioned a world where humans could rise above traffic jams and gridlocked cities, but the technological, economic, and societal hurdles loomed too large. It wasn't until the dawn of the 21st century, with advancements in energy storage, artificial intelligence, and materials science, that the dream began to take shape. Yet even as innovators like Dr. Elena Rios dared to reimagine transportation, they were met with resistance from every direction. Energy constraints, engineering limitations, and deep-seated societal skepticism made the early years of flying car development an uphill battle. The energy dilemma. One of the earliest and most significant challenges was energy. For a vehicle to take off, hover, and fly safely, it required a power source that was both lightweight and capable of sustaining immense output. Traditional internal combustion engines were not only too heavy but also noisy and environmentally unsustainable. Electric batteries seemed like a natural solution, but early designs proved woefully inadequate. "Elena, we're running out of juice after just 5 minutes of hover time," one engineer had said during an early prototype test. The room had fallen silent as the implications sunk in. Battery technology at the time simply couldn't meet the demands of flight. Engineers needed energy-dense batteries capable of delivering power for extended periods without adding excessive weight. The turning point came with the advent of graphene-infused batteries, ultralight, durable, and capable of storing unprecedented amounts of energy. By leveraging this cutting-edge material, Elena's team was able to create a power source that not only made sustained flight possible but also addressed environmental concerns. Still, there were other technical hurdles. Efficient energy use required breakthroughs in aerodynamics and propulsion systems. Early models relied on large, noisy rotors that drew comparisons to helicopters, alienating potential consumers. It wasn't until engineers adopted ducted fan technology and implemented noise-canceling systems that flying cars became practical for urban environments. Design challenges. While energy was the backbone of the project, the body presented its own set of difficulties. Early flying car prototypes were bulky and unattractive, evoking more laughter than awe. One infamous prototype, nicknamed the Flying Brick, was a clunky metal box with exposed rotors and a cockpit that looked more suited to a budget sci-fi movie than a futuristic transportation revolution. "If this is the future, I'd rather walk," quipped one skeptical journalist after a test demonstration. Elena and her team knew they needed a design that was both functional and appealing. Using carbon fiber composites and streamlined forms inspired by nature, they developed sleek, aerodynamic vehicles that could seamlessly integrate into the cityscape. The final designs looked less like science experiments and more like luxury sports cars with wings. Functionality was also paramount. Flying cars had to perform flawlessly in a variety of conditions, from gusty winds to torrential rain. Lidar sensors, advanced gyroscopes, and AI-driven stabilization systems were incorporated to ensure smooth, safe rides regardless of weather. Societal skepticism. Even as the technology evolved, society itself remained one of the biggest barriers to flying cars. The public had grown accustomed to terrestrial travel, and the idea of soaring above city streets evoked as much fear as excitement. People don't trust machines they can't control, Elena often said. Skeptics raised valid concerns. How would flying cars avoid mid-air collisions in crowded cities? Would they be affordable, or would they create a new divide between the wealthy and the rest of society? And most importantly, could people trust autonomous systems to safely ferry them across the skies? The answer to many of these questions lay in education and transparency. Elena's team organized public demonstrations, allowing people to experience the technology firsthand. Simulators gave potential customers a chance to fly in a virtual city, experiencing the seamless navigation and safety protocols that the AI County pilot offered. Governments also played a crucial role in addressing public skepticism. Regulatory agencies worked closely with manufacturers to establish stringent safety standards. Policies like mandatory geofencing in sensitive areas and real-time traffic monitoring helped reassure the public that flying cars wouldn't become an aerial free-for-all. The weight of expectation. While skeptics feared chaos in the skies, many in the industry feared failure. Investors demanded results, often pressuring engineers to cut corners. At one point, Elena's team faced a critical decision: rush the prototype into production to secure funding or delay the launch to ensure the vehicle met their safety and efficiency standards. "I'd rather fail honestly than succeed recklessly," Elena had told her board during a tense meeting. Her conviction paid off. The additional development time allowed the team to perfect critical systems, ensuring that the final product could deliver on its promises. Still, the weight of expectations was a heavy burden. The media, the public, and even the government scrutinized every test flight and press release. One high-profile accident during an early trial, a software glitch that caused a prototype to crash into an empty field, threatened to derail the project entirely. Elena faced the fallout head-on, addressing the media with candor and confidence. "Innovation comes with risk," she said, "but every failure is a lesson that brings us closer to success." Her honesty earned public trust, and the project pressed forward. The turning point. The true breakthrough came not from technology, but from vision. Elena's team realized that flying cars couldn't just be about solving traffic congestion, they had to offer a new way of life. The first full-scale public demonstration, held over the bustling streets of Tokyo, was designed to inspire awe. A fleet of flying cars rose gracefully from their vertiports, forming a choreographed display against the evening skyline. Below, citizens gathered in amazement, their skepticism giving way to excitement. The demonstration was more than a showcase of engineering prowess, it was a glimpse into the future. For the first time, people saw flying cars not as a distant dream, but as a tangible reality. By the time Elena stepped off the stage after the Tokyo demonstration, she knew the tides had turned. What had once seemed impossible, an urban sky filled with autonomous vehicles, was now within humanity's grasp. But as Elena looked up at the vehicles gliding silently through the air, she also knew this was just the beginning. The skies were open, and the future was waiting to be written. Chapter 3. The birth of eVTOLs. The birth of electric vertical takeoff and landing, eVTOL, vehicles marked a paradigm shift in urban mobility, transforming the way humanity approached transportation. What was once confined to science fiction, compact flying machines maneuvering gracefully through bustling cityscapes, became a plausible reality through the marriage of engineering ingenuity, environmental awareness, and the relentless pursuit of efficiency. eVTOLs weren't just vehicles, they were the harbingers of a new age in urban design and human mobility. From vision to viability, the idea of vertical takeoff and landing vehicles was not new. Helicopters had proven the concept decades earlier, but their noise, inefficiency, and reliance on fossil fuels rendered them impractical for mass adoption in urban environments. Enter the eVTOL, an aircraft designed to overcome these limitations using electric propulsion systems and advanced materials. The rise of eVTOLs began with a single question: how do we create a vehicle that can take off and land vertically, like a helicopter, but operate silently and efficiently in crowded cities? The answer required breakthroughs in three key areas: propulsion, energy storage, and materials science. 1. Propulsion systems. From rotors to fans, traditional helicopters relied on large, noisy rotors, but eVTOLs employed ducted fan technology to achieve lift and thrust. These enclosed fans reduced noise levels significantly, making them suitable for residential and urban areas. Additionally, distributed electric propulsion, where multiple small rotors operated independently, enhanced stability, efficiency, and safety. Each fan was powered by a high-torque electric motor, capable of instantaneous adjustments. This gave eVTOLs unprecedented maneuverability, allowing them to navigate complex urban environments with ease. In some models, tilt rotor technology allowed the same fans to provide both vertical and horizontal thrust. By transitioning seamlessly between hovering and forward flight, eVTOLs combined the efficiency of airplanes with the flexibility of helicopters. 2. The battery revolution. The Achilles heel of early eVTOL designs was energy. Achieving vertical lift required immense power, and early batteries simply couldn't store enough energy without adding prohibitive weight. The breakthrough came with the development of solid-state batteries and graphene-infused cells, which offered unparalleled energy density and rapid charging capabilities. For the first time, an eVTOL could fly up to 150 miles on a single charge, with fast charging stations providing a full recharge in under 30 minutes. These advancements not only made eVTOLs viable for urban commuting but also opened the door to intercity travel. Hydrogen fuel cells also emerged as a complementary technology, offering even greater range and sustainability. Unlike traditional fossil fuels, hydrogen produced only water as a byproduct, aligning perfectly with the growing emphasis on eco-friendly transportation. 3. Lightweight materials and aerodynamics. to maximize energy efficiency, eVTOLs needed to be as lightweight as possible without sacrificing safety. Engineers turned to advanced materials like carbon fiber composites and titanium alloys. These materials offered high strength-to-weight ratios, allowing for sleek, aerodynamic designs that minimized drag. Computer simulations and wind tunnel testing refined every curve and surface of the eVTOL, ensuring optimal performance. Designers took inspiration from nature, mimicking the streamlined shapes of birds and insects to create vehicles that moved effortlessly through the air. Revolutionizing urban mobility. With these technological breakthroughs, eVTOLs were no longer confined to research labs and prototypes. They began to redefine how cities functioned. Skylanes. The highways of the future. Cities adapted quickly to accommodate the new mode of transportation. Skylanes were introduced, altitude-based corridors that organized aerial traffic into efficient, structured flows. Low-altitude lanes served as local routes for residential neighborhoods, ensuring eVTOLs didn't interfere with cityscapes or low-rise buildings. Mid-altitude lanes handled urban commutes, connecting hubs like downtown districts and industrial areas. High-altitude lanes facilitated intercity travel, allowing eVTOLs to reach speeds of up to 200 miles per hour. An AI-driven air traffic control system managed these lanes, coordinating millions of eVTOLs in real time. Using quantum computing and blockchain, the system ensured congestion-free travel while prioritizing safety and efficiency. The rise of vertiports. Traditional airports gave way to vertiports, compact hubs designed for eVTOL takeoff, landing, and recharging. Vertiports were integrated into skyscrapers, shopping malls, and even suburban neighborhoods, making aerial travel as convenient as catching a bus or subway. Mega vertiports on city outskirts handled high-volume traffic, acting as hubs for long-distance commuters and freight services. These facilities also included maintenance bays and hydrogen refueling stations, ensuring the seamless operation of eVTOL fleets. Societal impact. eVTOLs didn't just transform transportation, they reshaped cities and lives. Traffic decongestion. Ground-level traffic diminished as commuters took to the skies. Highways once choked with vehicles were repurposed into green parks, bike paths, and pedestrian zones. Economic opportunities. The eVTOL revolution spurred innovation across industries, from battery manufacturing to AI-driven navigation systems. Jobs in design, maintenance, and vertiport management flourished. Accessibility. Initially seen as a luxury, eVTOLs became increasingly affordable through public-private partnerships. Governments subsidized sky taxis, ensuring that even low-income communities could benefit from the new technology. However, the shift wasn't without challenges. Critics warned of potential noise pollution, cybersecurity risks, and the exacerbation of urban inequality. Elena Rios, one of the foremost pioneers of eVTOL technology, addressed these concerns head-on. Every innovation comes with its share of challenges, she said during a global summit on urban mobility. But the potential of eVTOLs to democratize the skies far outweighs the risks. It's our responsibility to ensure this technology uplifts everyone, not just the privileged few. The future beckons. By the late 2030s, eVTOLs were no longer a novelty, they were a necessity. From London to Lagos, New York to New Delhi, the skies above the world's cities buzzed with activity. eVTOLs became a symbol of human ingenuity and resilience, proving that even the most audacious dreams could become reality. As the technology evolved, the vision expanded. Engineers imagined hybrid eVTOLs capable of crossing oceans, solar-powered variants for sustainable tourism, and even autonomous ambulances that could reach patients in record time. The birth of eVTOLs wasn't just the creation of a new vehicle, it was the dawn of a new era. Urban mobility was no longer limited by the constraints of roads and traffic. Humanity had taken to the skies, not with wings, but with the promise of a future where transportation was faster, cleaner, and more equitable than ever before.